So we're particularly interested in how a liquid may contact a solid and the properties of that interface. It's something that we would call interfacial engineering. By modifying the properties of a surface, both the chemistry of the surface and maybe the physical structure of the surface, you can actually have dramatic changes in the properties of the overall system. So that's something we experience maybe in the flow of a liquid past a boat, the flow of air past an aeroplane, maybe how ice contacts a surface. In each of these cases, it's really about what happens at the interface, how the liquid or the flowing material contacts a rigid material. And by changing both the chemistry and the physics of that, we can actually dramatically change the properties. I think one of the things we're really interested in at the moment is the possibility of using this control of a surface to actually change how water condenses on a surface. And we think of this in particular with application to fog harvesting. So if we're in a fog, we're really surrounded by a cloud of naturally desalinated water. So the sun heats the ocean, the water leaves the ocean, it comes away typically without a large part of its salt or its impurities. If we can control how that water actually condenses on a surface and then collect that, then you can think about farming or harvesting that water. And that's like a natural thermally driven desalination process. What we're trying to do here is think about being inspired by nature, how nature, some insects have patterned their surfaces to try and control where water droplets nucleate. We're trying to think about maybe doing that on a large scale, and by collecting that water we might actually be able to use it for farming, for reforestation projects, or even for commercial processes like mining. This is something that might be very useful particularly in areas like high deserts. Chile is a good example of that, but the Saudi Arabian Peninsula is another one where you have a natural desert area with very little water, but it happens to be adjacent to a very large body of water with a prevailing wind that blows clouds in the morning. And so if we think about how we might be able to pattern the surface, collect the water droplets, and then have them naturally run into a collector, we might actually be able to harvest that water. What we really take from nature is to try and understand on the microscopic scale what the physics is that's going on. So we try and understand the forces that are acting on the surface, how they balance at equilibrium, or if the system's out of equilibrium, how they control properties such as the flow or the friction on the surface. And by understanding the physics and the basic equations, those equations apply at any scale, and so we should be able to use them on larger surfaces as well as on, say, the scale of a feather or on a leaf. So rather than trying to exactly copy the structure, what we try and do is understand the basic equations or the basic underlying physics that apply, and then use those ideas. We might even be able to improve on nature. In the cases where we can't improve on it, we might be able to do a bad copy of it, but a good enough copy to do on a larger scale. So we don't try and exactly copy this, but just take the basic principles. And those principles are governed by the equations of motion and the equations that control, say, the shape of a liquid droplet on a surface, or the forces that control how liquids attach to surfaces. I think the broadest application area is really in this idea of structuring surfaces to either make them very phobic to something, such as a liquid, or maybe very philic to something, which means very loving of that material. So, for example, an anti-fogging surface that you might be interested in is something that really likes to be wetted by the material. If you want something that's self-cleaning, you might want it to be very hydrophobic. You want the droplets to run right off the surface. We're particularly interested in maybe trying to do this on glass, on a transparent surface, so that maybe you can develop glass coatings that allow the light or improve the amount of light that's transmitted, but also prevent fouling by sand or by biological deposits. So the application there might be, for example, the coating of solar cells. So you want your solar cells to operate year-round without having to be cleaned. You want them to let as much light through as possible, but you also don't want them to get dirty. So you'd like them to clean themselves, ideally. On a much smaller scale, if we're interested in oils, we as human beings tend to secrete all sorts of lipids and other biological oils. And so everybody's left a greasy fingerprint on a cell phone. Ideally, what we might like is a coating or for the glass that would allow us to make the fingerprints come off more easily.